-1. So we've done it. We've now defined what cosine is. And this is what it looks like. In this video, I'll provide you a quick refresher of a few basic facts about circles in geometry, explain what sine and cosine are, then apply algebra, which you already know, to derive equations for sine and cosine. Don't worry, to make sure you can follow along, I'll provide a quick refresher of algebra as well, starting with explaining why we always solve for 0, how that's useful, how that relates to the fundamental theorem of algebra, and how we'll use that to derive a formula for cosine and sine. I'll also introduce you to a mathematical notation for multiplying, which you should have learned in algebra, but probably didn't. So let's get into it. In order to start our discussion on trigonometry, we're going to have to take a quick look at a little bit of geometry first, and only a little bit. If we want to construct a circle, how do we do that? Well, first we take a line like this one here. We fix it on one point, let's say this point, and then we drag that line around until we get back to where we started. So let's start it. Right? Whenever we do this, the line segment that we're using to construct this is called the radius. And this distance here is what A represents over here. And that distance is going to end up being what by the time it gets to the end? Well, if this length here is 1, which it is, by the time we get to the end, A is going to be the circumference of this. And if you recall, the circumference of a circle is 2 pi r, where in this case the radius is 1, and therefore the circumference is 2 pi. Whenever we measure distance like this around a circle, we call the measurement of that distance radians. So this is 2.399 radians. So let's say we have the circle completed. Let's apply some axis. So let's add a line right through it. Right? It's centered at 0 on this line. So if we slice it in half with this line, what is this top half measurement, right? From this point all the way here. Well, if this entire thing is 2 pi, and we've cut that in half, then this length on top is just pi. Let's add another line here. So this is Cartesian coordinates, which we're familiar with. And I've sliced this circle again. And that tells us if this distance from this point all the way over here was pi, and we've cut that in half again, what distance would we travel from this point up to here? Well, just pi divided by 2. The only value that we're actually entering, because this is constant, is this. And once we do that, because we're now on a Cartesian coordinate system, we could actually measure the distance from down here to this point and the distance from over here to that point. 2 other measurements that we can look at that are dependent on this distance. Notice how the red line that measures the height and the orange line that measures the width keep changing. When one gets shorter, the other one gets longer. They go to 0 at one point. For example, the red line, the height, was just 0, and now the width is 0. And this continues on and on. So the measurements that we're looking at of height and width, those are actually what we're talking about when we're talking about sine and cosine. So let's pause it there. Let's add an entire circle around here. And the distance here, this green distance, we could also call that the angle. The height here is referred to as the sine. The width from this point over there is called the cosine. I've given you some distance that you've traveled along this circle. What at that point is going to be the height of this line and the width of this one? That's all sine and cosine is talking about. And when we talk about radians, we're talking about the distance we travel along a unit circle. So how are we going to define sine and cosine? So given this angle, what is the sine and the cosine? Let's use our knowledge of algebra to actually determine what these lengths are given this. So we're saying we have a function where the input value here determines these other things. So we have an independent and a dependent variable. The first thing we do is we remember something called the fundamental theorem of algebra. So what does the fundamental theorem of algebra tell us? Well, it tells us if we have a polynomial, for example, this one, if we look at it and look for the highest term for our variable, in this case 2, that's going to be the number of zeros our function has. Why do we care about that? Why do we solve for 0 in the first place? Well, it turns out if we know where this function is 0, we could actually define the behavior everywhere else. For example, we see on the graph here we have a 0 at x is equal to -2, and we have a 0 at x is equal to 1. So how do we use that to our advantage? Well, the first thing we do is, let's take that off here. We move the -2 to the other side by adding 2, like that, and we move the 1 to the other side by subtracting 1, like that. This up here becomes 0. This down here becomes 0. And we have two equations that we actually now have to multiply by each other of x minus 1 and x plus 2. And that gives us the entire function that we need. We call these the roots, right? Because that allows us to determine, like the roots of a tree, everything grows from that. The roots of a function allow us to multiply out the zeros together and find the behavior everywhere else. So let's take a look at another example. Let's say we have x cubed, right? That looks like it only has one zero. Well, if we say x is equal to 0, and x is equal to 0, and x is equal to 0, we move the zeros to the other side. Then we multiply the zeros together. So x plus 0 times x plus 0 times x plus 0. So in fact, we did have 3 zeros. They just were duplicate. And sometimes the zeros might not even be on this line, right? It might not be anywhere in sight. What do I mean by that? Well, let's take a look at a different example. Let's remove that one. Let's say we have something like x to the 4th plus x cubed minus x squared plus x minus 2. This looks a little strange, doesn't it? It looks like we only have 2 zeros, but we know we have to have at least 4. Let's include the first 2 zeros that we can see. X is equal to -2, and x is equal to 1. Let's do the same thing as before. We go ahead and subtract 1 from both sides. This becomes 0. Add 2 to both sides, becomes a 0. Now we multiply these 2 zeros that we could check here and know together. So that does not give us the same behavior. We obviously have some other 0 that we can't see. Maybe it's a duplicate 0, maybe not. But I'll just tell you, this is the completed version. So what did I do here? Well, this doesn't quite look like what we would expect. This is actually 2 zeros and 1. But those zeros will not appear anywhere on this graph. We won't be able to see it here. And why is that? Well, let's solve this for 0. X squared plus 1 equals 0. We move the 1 to the other side. We get x squared is equal to -1. Take the square root of both sides to get x. And x is equal to the square root of -1. But because this is a square root, it's plus or minus. So our completed version would be this. This isn't graphed out. And the reason is this software does not have the ability to graph this. Whenever we get a -1 and take the square root of it, this is a number that we call an imaginary number, because there's really no number we can think of that whenever you multiply it by itself, it gives you a negative number, right? A negative times a negative is a positive, and a positive times a positive is a positive. Due to the fundamental theorem of algebra, we know we have the 4 zeros in this case, and if we allow imaginary numbers, we could represent any function as a product of its zeros multiplied by some constant. In this case, the constant was 1. That consequence of the fundamental theorem of algebra is called the Weierstrass factorization theorem. How useful is that? Well, if we go back to our diagram here, we know that at certain times this height is 0, and at certain times this width is 0. And if we know when those are 0, we could use that by multiplying all their zeros out in the same way we just did to find out what the function is everywhere else. So whenever it's 0, we could determine what it would be here, for example, or anywhere else, right? We would now know the height everywhere and the width everywhere given this length here. So starting at 0, the height is 0, Then we go up here. This is pi halves. At pi halves, the width is 0. And then we go down again. This distance over here is pi to here. And the height is 0 again. When we do this over and over and over again, we get one 0 after another, right? And we could go in the circle forever. So that tells us we have infinitely many zeros, right? Infinite is this, it's like forever, right? We just do that over and over again. So you're thinking, well, how can I multiply infinitely many zeros together to get something that makes sense? Well, let's first worry about finding what those values are when it's 0, right? Let's look at the width first. When is the width 0? So let's start from the beginning here. We're moving up. The width was 1. Now it's going to be 0 here at pi halves. And then it goes down. It's not going to be 0 again until it's down here. We know this whole distance is pi. So pi halves plus pi. Let's pause that. So pi over 2 plus pi. How do we combine that? Well, we multiply this by 2 and then divide by 2. And then we could add them together because the denominator is the same. Right? Pi plus 2 pi is equal to 3 pi halves. So that's whenever it's down here. That's the distance this green line has traveled whenever this is 0. And then we continue it on. And then from this point to up here, that's another pi. So plus pi. It's 5. First we started with pi halves. We added pi to get 3 pi over 2. We added pi again to get 5 pi over 2. Do you see a pattern here? Well, let's add pi again. That's the next point where this function of the width is going to be 0. So 5 pi over 2 plus pi. So that's going to be 7 pi over 2. So it's predictable. We know exactly where these zeros are going to be. But wait, we could also go the opposite direction, right? We don't have to start going this way. If we start moving this way, this is the negative direction, right? If this is positive distance, we could say this is the negative distance, that we're going the opposite direction. So in that case, if we go from here down to here, it's negative pi halves. So we also have negative pi over 2. And then we go again a more negative direction in this way by pi. So we add a negative pi. And we continue that. So the exact same thing, except for all the signs are negative. I'm saying with the fundamental theorem of algebra by our side, we could take all these points that are 0. We could do the same kind of tricks we did over here. But in order to do that, we're going to have to look at a notation that allows us to represent that in a manner that's compact. So we need a way to represent a lot of things multiplied by each other in a very compact way. In order to do that, we'll have to develop a new notation that makes sense and allows us to do that. So let's start with something simple like 3 to the 5. We're just going to say that's equal to, well, 3 times 3 times 3 times 3 times 3. And that's going to be equal to a product, right? A product is just something multiplied by something else. So we could actually remove that 3 to the 5, shift that over, and say we have a product which is equal to 3 times 3 times 3 times 3 times 3. Looking at this, we can see that we have 5 things, and it might be helpful to know how many things we have, especially if we have a lot of them. So if we track where each thing is, we have our product input 3, 3, 3, 3, 3, and we have a position for each of those inputs. So let's say we have a product input and a position. So in the first position of our product, we have a 3. In the second position, we have a 3. In the third position of the product, we have a 3, and so on. So for example, if we had a different type of product, we have a product input and a position where our position happens to be 1, 2, 3, 4, 5, and the input for that position is 1, 2, 3, 4, 5. So we have a product, and that's equal to, okay, so those are the 3 types of examples that we can deal with. So let's look at the first one, where we have a product of the same thing multiplied by itself some number of times. And that number of times is easier to look at in this table, where we have the product input and its position. So let's represent we have a product by using this pi symbol. This just means we're taking the product of some input. And we need to include in that the positions. So we're going to start at position 1. Let's just say p is equal to 1. And we have a total of 5 positions, so we're going to start from p is equal to 1 and go all the way to p is equal to 5. So in this case, what is that input? Well, in each case, the input's the same, and it just happens to be 3. So that's going to be equal to 3 to the 5. So we have a new notation here that happens to let us do something we already know how to do. So how is that going to help? Well, let's take a look at another example where we have a product input that does not have the same number in each position. So again, we have a product of some input, and we know that ranges from 1 all the way up to 5. But now what do we put in this input? Right? In the first position, we have a 1. In the second position, we have a 2. In the third position, we have a 3. So for every position we have, that's also the same input. So we could just put our position as the input. So this notation allows us to do that, where we could start at p is equal to 1 and input each position number. And that's just going to be equal to 1 times 2 times 3 times 4 times 5. With this, we now have a useful representation that allows us to represent a string of things, like 1, 2, 3, 4, 5, multiplied by each other, in a very compact way. You cannot do the same thing with the standard 3 to the 5. So this is now something completely different, but it can do the same thing as exponentiation whenever that exponent is a whole number. Let's take another table of 1, 3, 5, 7, and 9. We want to multiply those things out. In this sequence, the position of 1 is first position, the second number has a 3, and so forth. So how do we figure that out? Well, we have a product of some input, and those inputs have positions that range from the first one to the fifth one. But now, what do we put for that input? Well, we just saw if we put the input in terms of our position, we could put that information in front of this product sign and use it. So let's take a look at our position values. Well, they're sequential, 1, 2, 3, 4, and 5. They go odd, even, odd, even, odd. The values we want to multiply together and put that in our notation are all odd. What do we know about even and odd numbers? Well, every even number is sandwiched between an odd number. So if we want to have strictly odd numbers, how can we do that? Well, if we multiply our position number by 2, that will make all those numbers even. And then an even number will be either 1 above or 1 below an odd number. And let's compare these numbers to the numbers that we want to multiply together. Well, it looks like they are all 1 off from that number. They're 1 above it. So we need to subtract 1 from each of them, and that will give us our odd numbers. And that's 2p minus 1. So we have to go ahead, if we want to represent this in terms of our product notation down here, as 2p minus 1. And that allows us to get exactly what we want, which is 1 times 3 times 5 times 7 times 9. And that's how we could represent a series of odd numbers multiplied together using this notation. So let's think about that. Remember we said we have our zeros of pi over 2, 3 pi over 2, 5 pi over 2. And those are when the width is 0. And that continues on forever. And those are just the positive. That's just going counterclockwise around the circle. So if we want to compactify that and represent all those numbers in one expression that we could easily determine the first 0, the 10th 0, the millionth 0, how would we do that? Well, let's start by designating each one of those as having some position. It's the first 0, it's the second 0, it's the third 0, and so on, like that. So we could actually do exactly what we just did. We could define our positive zeros equal to 2 times the position minus 1 multiplied by pi divided by 2 if we're going counterclockwise. But we could also go clockwise, in which case we're going our negative direction, and we have negative zeros, which were the same thing with a negative symbol in front of them. So now we've compactified infinitely many zeros into 2 expressions. So let's go ahead and actually use those expressions. What we're trying to do is find what this value is no matter what input we give it. So we always want to know what that value is, even though we have almost no way of knowing it except for knowing that it's 0 at the certain values we've already determined. Because this is a Cartesian coordinate system, let's say that the input we're giving it is x. We're giving it some value. And that's the value we're going to input into it. So we know that's the distance we're going around. So let's say we know we're going around counterclockwise. So that means we have 2p minus 1 times pi divided by 2. Those are the zeros that we'll get where p is any number that's a whole number and positive, and we have the negative set where x is equal to negative 2p going counterclockwise. And I'm saying that these are zeros of it, and p goes on forever. It could be any value as long as it's positive and a whole number of 1 or greater. We're going to do something very similar to what we did with the algebraic functions. But first, let's divide everything by this value. So we're going to shift it over to the other side. Right, so that gives us x over 2p minus 1 times pi over 2 is equal to 1. And now we'll subtract 1 from each side to give us this expression is equal to 0. Okay, let's do the same thing over here. That's equal to 1. We've divided over here. Now we have that. We subtract 1 from both sides. Those give us our zeros. And just like before, we're going to have to multiply these zeros together. But this time, the difference is we're going to have to use the product notation that we've just learned. So let's say we're starting from 1, and we're going to what? Well, we said it goes on forever and ever, but we can't obviously put that in here. So let's just say it goes on a lot. Let's just pick a really large number and say that should be good enough, right? And now let's go ahead. Theoretically, we've graphed it, so we're going to get a graph going along the x-axis here. So instead of the radians being drawn out like this, we're drawing the radians in a straight line. So whenever we have 6 radians or we have 2 radians or whatever radians, we're going to have traveled this distance. So let's go ahead, and there we go. So only knowing those zeros, we were actually able to determine the value everywhere else. So for example, at pi over here, we have -1. So if we go back to our circle, indeed, we've traveled pi distance around this circle. And this width here is -1. So we've done it. We've now defined what cosine is. And this is what it looks like. It starts at 1, it goes down to 0, it goes down to -1, and then it starts going back up to 3 pi halves, which is at 0 again. So we've gone 2 pi distance, and it's back to 1. If we go the opposite direction, we get the exact same thing. So that's actually how we calculate out cosine. Whenever we need to know that distance of any value, we just multiply out all the zeros that we know. Using algebra, we're able to do that. Now, we're supposed to go on forever, but we know we can't do that. So we just pick a large enough number and stop. So naturally, that would give us some issues with accuracy further down here. But those are issues that we could solve with other techniques. In fact, we often don't use this kind of notation because after we learn calculus, we get better ways of computing this out. But for now, because we started with algebra, that's how we're going to do it, because it just builds on what we already know. We also said we could calculate the height. Of course, at 0, we haven't moved anywhere, so the height is 0. So let's create our own little list here of the height zeros. So the first one is at 0, and we go over here. It's getting smaller and smaller and smaller, and finally it's 0 when we've traveled pi distance. So let's say that is pi. We keep going around, and it's back to 0 when we hit 2 pi. Again, we go all the way around and around and around. We add pi to that. So then by the time we get here, that's going to be 3 pi. And again, so that's going to be 4 pi. Now let's go the other direction. We're going clockwise, so we're going the negative direction. That's what we're designating it. So we get another set of zeros that not start with 0 because that's already included in the other set when we started going the other direction. So it's -pi, -2 pi, -3 pi, and so on. So we have our 3 sets of zeros in this case. So let's combine them all. First, we'll go ahead and divide out. So we get 1 on this side, and the p times pi on the other. Then we subtract 1 from both sides. We get our equation of x divided by p times pi minus 1 is equal to 0. We do the same thing, and we get our next set of zeros of x divided by negative p pi minus 1. So we move those zeros down here. We don't need any of this. And everything multiplied by a 0 is going to be 0, so we don't even need that. But now what do? Well, the same thing. We set up our product of p starting at 1 and going to some large value. And why didn't I include this x in here? Well, because these x's are only over here because they have repeating zeros at these values when p is a whole number of 1 or greater. This didn't, so it's kind of different because it doesn't have a recurring theme. It's only there once, and that's it. So let's go ahead. We get it graphed out, and that's what that looks like. That's all thanks to our good fundamental theorem of algebra and a little bit of modeling skills. And of course, the product notation, which you probably never learned, but absolutely should have learned. That's how we define sine and cosine, where the height here is the sine, the width here is the cosine. The value that we're putting it in when we're taking the cosine or the sine of something is just the distance that we've traveled along a unit circle. And what other features can we derive from that? Well, we've been drawing this line here, and that's what we've been using. It's constant. But one thing that's not constant about that line is its slope, right? I'm moving it around, and its slope is changing. Its length is not changing, but its slope is. So how would we determine the slope? Well, if you recall, the distance down here is the same as the distance up here. Whenever we have a line, how do we calculate that slope? We know that that line has a slope that's rise over run. That's what we probably learned. So we just have the rise, which is this height, over the run, which is this distance, which is the same as this distance. In order to determine the slope of this line, we simply take the sine and divide it by the cosine. And that gives us what slope we'll have whenever we travel some number of radians around. Now, what we call that slope is the tangent. So those are the things that we talk about when we're dealing with trigonometry in the most basic sense. Now, you might have heard something different, something probably completely different, like SOH CAH TOA or something like that. And frankly, I don't find that to be a helpful introduction. So where did we get that SOH CAH TOA stuff? And how does this apply to triangles? Well, it's pretty simple, but that's going to have to wait till next time.